only about 30 years old and badly corroded and was being replaced. The good thing is, in this particular situation, they didn't want to repeat the same mistake, so this particular bridge ended up having pozzolans as well as a corrosion inhibitor in it. But a lot of times, as designers, one of the things that we focus on is the initial cost of the concrete. And that is not a smart thing to do. We need to look at the life cycle cost and make decisions based on life cycle cost. Because a lot of times when we're designing for durability or for and so on, what's going to happen is the durability enhancing options are essentially value added options. And as a result of that, they will have initial higher concrete cost. So if you take a cubic meter of concrete of the option with the durability enhancing materials, it will be higher. However, the in-place cost and the life cycle costs are typically much, much lower. So we need to be able to look at the life cycle costs in making decisions. Other thing is, what are the durability alternatives that are available? Either different concreting options, such as using geopolymers, reinforcement options, or even non-concrete options, such as increasing concrete cover. So the key strategy, you heard it on Wednesday, you heard it yesterday, and you're going to hear it again from me today. Durability-based design is the way to go to help achieve the design service life with minimal repairs, if any. Now, some of you may have seen these pictures that I showed earlier, but I like to use that to illustrate the high cost of corrosion. This building is called the Miami Building in San Juan, Puerto Rico. I took a picture of it in 1992 when we had the ACI convention over there. And at the time, you can see the upper floors were badly corroded and it was being repaired. 10 years later, about 10 years later, I went back and the corrosion has started on the upper floors again. And it was also being repaired. 2019, I went back there, it started on the upper level again, as you can see here. Essentially, it's the gift that keeps on giving. And if you're the owner of this particular structure, pretty much every 10 years, you're going to be repairing it. That is not ideal. That is not sustainable. That's not the way to go. So we need to make sure we look at the environment in designing these buildings. Now, what are some of the options that are available? Using supplementary cementitious materials. Yesterday, we had the presentation on LC3. It's essentially a ternary blend material. Limestone calcine clay is a ternary blend material. Now, this is a study that was done by Professor Mike Thomas and his colleagues, where they looked at ordinary Portland cement and different supplementary cementitious materials, and also included a ternary blend, as you can see here. So fly ash, silica fume, and then this is a combination of fly ash and silica fume. And you can see the significant decrease in the diffusion coefficient of the concrete. Now, what's the benefit? Using numerical modeling to predict the ingress of chloride into concrete with these diffusion coefficients, this was what they came up with. Ordinary Portland cement, as you can see, and if you have a concrete cover of 60 millimeters, you can see that you already have more than enough chloride to initiate corrosion. This is where silica fume and fly ash on their study basically ended up tracking one another, but very good. And then you look at the combination of silica fume and fly ash, where essentially you're shutting down the permeability of the concrete. So if you have the option to use a ternary blend, always go with it. And what we saw pretty much the same thing yesterday from the LC3 presentation, where the LC3 had very low diffusion coefficient, because in effect, what you have in there is also a ternary blend. Now, beyond that, the other thing will be to specify appropriate durability enhancing materials, such as corrosion inhibitors or other types of materials. Currently, the ACI 318 building code permits the use of corrosion inhibitors that meet ASTM-C 1582 criteria. So those are also available. And there are tools that are available that can be used to really assess the benefit of all of these materials. And these are service life prediction models. There's a Life 365, which is a free software. You can actually download it from the internet. Just type in Life 365, software, and you can download it. And then there's also Stadium. Stadium requires a subscription. So the easy thing to do is to go with Life 365. But using Life 365, you can look at different options. Right now, it allows you to go up to 6 different options. And you can look at different options, compare them to your base case to see what impact they have in terms of the years to, in terms of time to initiation, as well as on the top over here will be time to repair. The time to repair is typically 6 years from when corrosion actually initiates. So this is something that you can use to assess the corrosion service life of different options that you have for concreting. And this is looking at the options without corrosion inhibitors. And when I add a corrosion inhibitor to it, in this case, a calcium nitride-based corrosion inhibitor at 20 liters per meter cubed, you can see the increases that you get in corrosion service life. And with option number 6, now we're looking at about 150 years in terms of corrosion service life. Option number 6 previously, was giving us about 50 years of service life. But then the addition of the corrosion inhibitor takes it all the way up now to 150. So these are things that you can do, in terms of modeling the corrosion surface life that's available. Now, this is a perfect example. This is a Confederation Bridge in Canada, Prince Edward Island. And this was built back in 1997, so quite a while back. And one of the things that was very interesting at the time was the specification actually included a diffusion coefficient. So it wasn't just the compressive strength of the concrete, but then the concrete had to meet a specified diffusion coefficient, which based on analysis will help them achieve an extended service life of over 100 years. And this was the first of its type application in Canada. Now, the durability issues that they also considered with this particular bridge included abrasion and impact of ice on the piers. So they actually, you can see here, they have ice caps over here, to protect the concrete. Corrosion of reinforcement, of obviously being in a marine environment. They also were concerned about alkali aggregate reactivity and sulfate attack. And then being in Canada, freezing and thawing resistance, as well as scaling resistance. So these were all the things that the design engineers considered, before, during the design of this particular bridge. And there were parameters that were set to make sure the durability will not be compromised over the desired service life of the concrete. Now, this slide basically says we have issues. Now, why is that? Even though we have all of these durability enhancing technologies, they are typically not used. Why is that? Because they're either not specified, or as I indicated earlier, the focus is on initial cost instead of life cycle cost. And then beyond that, we also have the situation of resistance to change. No, I've always done it this way. We've always done it this way, especially when I talk to the departments of transportation, the engineers over there. This is the way we've always done it. And it's very unfortunate, but relatively, the concrete industry has a poor record of accepting new technologies. It's true. There are new technologies out there, but the concrete industry is very conservative and has a poor record of accepting new technologies. Now, next thing will be to specify sustainable concrete. So looking at Portland cement reduction, aggregates, permitting the use of recycled aggregates where feasible. Right now in North America, there's a startup company that is manufacturing synthetic aggregates from sequestered CO2 that's been sequestered. Really, really interesting. If they're successful, you could end up in a situation where the concrete would actually be net negative with respect to CO2 emissions because of all the CO2 that will be sequestered, within the aggregates. Other things are also reuse of retained fresh concrete, and ASTM has a new standard that permits the reuse of retained fresh concrete in a new batch of concrete. And all of this is to help minimize concrete waste, which again goes towards sustainable use of concrete. Caltrans, California, DOT, again being very progressive, or has already incorporated this into their specifications, permitting the use of retained fresh concrete. The next thing is the specifications should be performance-based, not prescriptive. And what do I mean by that? As engineers, what we need to do is to specify the required performance, including the service life of the structure and so on, and essentially allow the contractor and the concrete producer to provide the concrete mixture that meets the specified performance requirements. Now, one of the things that Caltrans did back in 2010 was they amended their specification. What were some of the things that they did? Previously, they had a requirement in there that the Portland cement content had to be greater than 75%. They removed it. They also had limitations on the amount of fly ash that could be used. They also took that out. And they ended up permitting the use of up to 3 binder materials because they recognized the significant impact of ternary blends in terms of improving the durability of concrete. Unfortunately, when we replace a lot of the Portland cement, when you look at a lot of studies that have been done, normally people talk about retardation of early age strength. So you have early age strength development issues, and then also retardation of the time of set of the concrete. Now, that's what's going to happen if you don't optimize the mix. If you simply take out Portland cement and put in fly ash and slag cement and so on, that's what's going to happen. It will affect your early strength development and you'll get retardation. When you're doing these things, you need to optimize the concrete mixture and look at the use of chemical admixtures and so on in order to make sure that the early strength development and the time of set are not compromised significantly. Now, one of the, I have this publication, I put this in here, let me go back. There's this bulletin on specifying sustainable concrete from the Concrete Center in the UK. It's a very good resource for structural engineers, for designers, and it tells you basically some of the things that you need to do. Now, what do they include? Things such as having a balance between the reduction of embodied CO2 and the design, specification, construction, method, and contract programs that need to be done at the early stage. So these are some of the guidelines that they have in this particular booklet. So I would recommend that you just Google it, specifying sustainable concrete from the Concrete Center, and get a copy of it. It's got some very useful information in there. Now, that said, these are examples of some low carbon concrete projects that we've worked on. And these are iconic towers in New York City. These are the World Trade Center replacement towers. What is very unique about these towers is the fact that up to 74% of the Portland cement was replaced using fly ash, slag cement, and silica fume. And it basically, these concrete mixes were extremely high strength concrete, and they had very high modulus of plasticity because of the stiffness that was required. Essentially, the difference, however, was these concretes were proportioned and adjusted with chemical admixtures, so they had very little impact on the operations of the contractor. But this is using existing technologies, fly ash, slag cement, and silica fume. This is the 432 Park Avenue, also in New York City. It's a very slender architectural building occupying one block. And up to 74% of the Portland cement was also replaced using these materials. But instead of silica fume, we ended up using metakaolin because they needed to have a white color. And then we used white cement instead of gray cement. This is in San Francisco, up to 70% SCM replacement using just slag cement. What I'm trying to get across to you is we know currently how to proportion concrete to have low embodied carbon. It takes expertise, it takes knowledge of on how to use chemical admixtures, as well as how to proportion these mixes to be able to balance the needs of the contractor with the needs of the structural designer. This was a project that was done just recently in Chicago, and again employed low carbon concrete. Replacement levels ranged from 65 to 73%, and it involved approximately 21,000 cubic meters of concrete. But this was a quote from one of the executive managers of Lend-Lease. He basically said, low carbon concrete and sustainable features in general are highly marketable. Increasingly, clients and investors are seeking sustainable building construction, and they are often even willing to pay more for it. All of this is being driven by owners. Now, for the Reed residential tower, they were able to quantify the sustainability benefits of the concretes that they used and basically put them in terms that the average person would understand. So the CO2 savings that they got, they basically predicted will be equivalent to the CO2 emissions coming from burning about 260,000 liters of gasoline, or let's say you can avoiding equivalent to greenhouse gas emissions avoided by, let's say, almost 26,000 trash bags of waste that's recycled inside of landfill. So typically in these analyses, we try to put them in terms that the ordinary person can relate to, instead of kilograms of CO2 or things of that nature. The bottom line is owners are currently driving the use of low carbon concretes in North America. So we saw the Port Authority of New York, New Jersey, the Public Utilities Commission of San Francisco. They are driving the use of low carbon concretes. And then the other thing that I also want to leave you with in terms of potential low carbon concrete strategies is improving constructability, and I'll talk more about it later on. But this is to make sure that we minimize the likelihood of construction errors and then also improve construction productivity. It's very, very critical. My predecessor, Kari Kopczynski, who was president last year, basically took this as his mission. And he made a quote that I have over here. It says, constructability involves incorporating construction knowledge into the design process to improve construction productivity. When architects and engineers acquire a working knowledge of construction and then collaborate with the contractor and subcontractors during design, magic happens. And it's true. We need to be more aware of construction practices and so on. Now, ACI now has on its agenda the goal of offering a certificate program, a certificate training program on construction productivity. And it would include training modules that will provide designers with a working knowledge of formwork, reinforcing bar detailing, specifying concrete, differences in the ways design should be approached as a function of project delivery type, and many, many more subjects. So be on the lookout for these. I'm going to finish up now and talk about some recent advancements at ACI. Now, ACI was founded in 1904, basically as a professional society. It's not a trade association. And the vision of ACI is essentially a future where everyone has the knowledge needed to use concrete effectively to meet the demands of a changing world. And our mission, similar to yours, is to develop, disseminate, and advance the adoption of our consensus-based knowledge on concrete and its uses. So that is the mission of our ACI. ACI has over 30,000 members worldwide, and we also have over 15,000 students. We have 93 chapters all over the globe, and also over 250 student chapters. So for me, this week, it's been very refreshing seeing all your students over here competing and so on. That's what we like to have our student chapters do. We have 58 international partners, and obviously IBRACON is one of our international partners. I think one of our very first, if I'm not mistaken here. And the building code, the ACI 318 building code, is used in over 60 countries. Now, one of the things that we're most proud of is our certification program. And to date, we've credentialed over 700,000 individuals in the concrete industry, all over the world, with respect to certifications. We also have select documents that are available in 15 languages. In terms of ACI resources, we're headquartered in Farmington Hills, Michigan. This is a roof of our headquarters building, and I'll talk about it a little bit. We have about 135 staff members, and we also have an international office in Dubai in the UAE, and we have regional offices in California, Illinois, and we're going to open a third one in the Baltimore, Washington area. But this is just a little bit of about ACI. Now, what are some of the things that we've done of late? In line with our mission to essentially help bring new technologies to use much faster, ACI has created a position of Director of Innovative Concrete Technology, and Dr. Rex Donahue, who most of you will know used to be the Editor-in-Chief of Concrete International. He's the inaugural director in this particular position. And his main mission is to help attract emerging technologies for development within ACI. Now, ACI has also formed centers of excellence. And the first one that we formed, was last year. It's the Center of Excellence for Non-Metallic Building Materials. And the mission of this particular center is to collaborate globally on the use of non-metallic building materials to drive research, education, awareness, and adoption. Saudi Aramco was the founding member of this particular Center of Excellence that we call NEXT. We also have ExxonMobil as well as MST Bar. It's an outfit in Canada, and they are currently they are the 3 dues-paying members of NEXT. So what is NEXT doing? They've been very, very active actually, essentially sending out requests for proposals, RFPs, and they're basically funding different types of research projects, all to advance the use of non-metallic materials. So for those of you in academia over here, just make sure you take a look at what Next is doing, and if you feel inclined, do send in a proposal to them. Okay. Now, in August of 2021, that was last year, ACI adopted a new position statement. And this position statement basically empowered ACI staff and leadership to support policy positions that encourage the establishment of criteria related to carbon neutrality of the built environment. And along with that, to also assist in the development and dissemination of information to transform the concrete industry into a carbon neutral industry. And in line with that, we formed our second Center of Excellence, and we call that NEW. So we have Next, and now we have NEW. And this is the Center of Excellence for carbon neutral concrete. And basically the mission is to collaborate globally to drive research, education, awareness, and adoption of the use of carbon neutral materials and technologies in the built environment. Now, these are going to be some of the core functions of NEW. Technology acceleration, coordination with ACI committees, technology transfer and professional development, but international and student outreach, But one of the biggest areas is technology assessment and validation. Why is this? There are a lot of entities, manufacturers that are coming up with technologies that they claim to be to help with lowering the carbon footprint of concrete. The issue that we have now is a lot of owners don't know how to essentially make decisions based on those based on the information that they're getting from these vendors. And what they're looking for is an independent entity to be able to assess these technologies and basically say, yes, this technology will do what is being claimed, or this technology is just not too good. So that's going to be one of the key things for the Center of Excellence NEW. And along with that, we also realize that there has to be a change in the culture of the concrete construction industry. Remember, I said previously that we're too conservative. So we need to change the culture and embrace new technologies. So in line with the need for validation, we've hired this gentleman called Dean Frank, and he's going to basically develop programs to assist in reducing carbon emissions in the construction industry. And primarily, he's going to be working with NEW, as well as also working with Next. So he's going to help spearhead our whole effort with assessment and validation of new technologies. Now, who are the new sponsors and partners? Basically, anyone who's involved in the concrete industry. And currently, these are the sustaining members that we have. And I'm sure you recognize some of those names. Meta, the parent company of Facebook. Breakthrough Energy. Breakthrough Energy is a financial arm of Bill Gates' empire. We're also more than likely will be bringing on Google and Twitter and some of those other entities very soon. All of these high-tech companies are very much looking at reducing their carbon footprints, and that's why they're coming to NEW. Okay. We also have some other supporting members, Baker Concrete Construction, and then we have various affiliate members. Now, this is a project that Meta did just back in April of this year. And what they ended up doing was they leveraged their resources with respect to artificial intelligence and worked with two professors at the University of Illinois, Urbana-Champaign, and a concrete producer to optimize the concrete producer's concrete mix and come up with a mix that had 40% lower carbon emissions. Essentially, Meta wants to walk the talk. I mean, they're putting their money, along, what they really believe in. And currently, if you go to Meta, with a new technology, they're going to ask you to go to new for validation and testing. Now, we've also signed